bell to tell you that your class recording has started. So you are now being recorded. All right. Way back on the second day of school, we were talking about physical science and what physical science was. And we talked about the idea that there are main topics, or we talked about the fact that there are main ideas that flow through physical science. And I called them the big ideas of physical science. Does anybody remember the four big ideas? Or let's say maybe one of the four big ideas of physical science. Anybody? I remember anyone? Someone go ahead. Energy is one of them. So let's save that one for last. So energy is one of those. Anna. Space and time. The universe is big and old. This universe that we study is big and old. Julia. Forces in motion. Forces in motion. Forces how things change and what causes things to change. Peyton. Matter and change. That we live in a big old universe, but the stuff that's in that big old universe is the same stuff. We just keep rearranging it. Right? Forces in energy is what causes the change. Forces in motion is what cause the change, and then energy is how that change occurs. Okay? So, today we're going to introduce different kinds of energy. What we will find is that at some time throughout the year, we are going to talk about all 6 of these different kinds of energy that I'm going to introduce to you today. Not in detail, obviously, as far as the introduction today, but we will talk about all 6 of these types of energy as we go along. There are some things that make them similar, but there are some things obviously that make them different, and we'll talk about the similarities and differences as we move along. But first, let's talk about energy in general, or not. Maybe my slider. There. All right. Selma, I'll ask you because you were the first one to say energy. Do you remember our real quick definition of how we define energy on the very second day of school? The ability to do stuff. Okay? The ability to do stuff. And do stuff is not very descriptive, which is fine. Okay? If you're looking for something that maybe sounds a little more, scientific or whatever, okay? Right? The ability to move or change matter. I believe your slides say the ability to move or change other objects. Okay? Same idea. So energy is this ability to move or change matter, right? And then Julia, you said that forces in motion, that's how we change things. So energy is the ability to change stuff. Forces is how we use that ability to actually change stuff. While all of these different types of energy are different, there are some things that make them similar. One of those things that make them similar is the unit that we measure energy in. The SI unit for energy is joules, and we abbreviate joules with a capital J. Joule is a derived unit. Do you remember derived unit from last unit? What it means to say something is a derived unit? That means? Okay. Andrew. What kind of units are formed together? Two base units. That's what I was thinking. Right? So when we talk about the joule, when we talk about the joule, okay, that combination of base units is represented by the capital letter J. If we have a very complex derived unit like the joule, okay, instead of writing kilograms times meters squared over seconds squared every single time we talk about energy, that's when we use the abbreviation, so we don't have to do that every single time. Now, that may not make much sense to you at all. It probably doesn't, okay? But that's the combination of base units that come together to give us what energy is, this ability to move or change matter. If you don't understand it now, don't worry, right? We'll get to it later on. Good there? All right. Like I said, there are things, that's how energy is similar, but there are things that make them very different. So let's talk about those things. Here's my slide. All right. So first, mechanical energy. Okay? Mechanical energy, by definition, is a dot on the board. All right. Mechanical energy is the energy associated with the motion and position of everyday objects. I'm assuming that if I asked you guys right now about energy, you would probably tell me about one of two forms of energy that you've studied up until this point. What are the two kinds of energy that you guys have studied so far? Paula? Kinetic and potential energy, right? Paula, what does kinetic energy deal with? When we say that something is kinetic, that means that it is, anybody else? That's the other one. Moving, all right? So that's the motion part of this section here, okay? And then the position part, you guys have probably learned about potential energy as stored energy. We're going to change that definition a little bit starting tomorrow because I don't like it. I don't think it tells you what it's supposed to tell you, okay? But mechanical energy is the total amount of an object's kinetic and potential energy. But we'll find out again tomorrow that there are actually two kinds of potential energy. One is called gravitational potential energy, and we represent that with the capital PE for potential energy, and then the subscript G for the gravitational part, so gravitational potential energy. And then there is elastic potential energy. So we still represent potential energy with the capital PE, but then we use the lowercase e to represent elastic. And that's funny because it says PE on the board. Yeah, if I don't say that, then somebody finally realizes it, and they start like whispering to the person next to them. Yes, it says PE. Let's just get it out there out in the open, and we have a good chuckle, and All right. So like I said, this is the kind of energy that probably you guys are most familiar with. And in this unit that we're starting off with, we're going to study this type of energy again and make sure we understand it and how it converts and stuff like that. But there are lots of other kinds of energy out there. For instance, thermal energy. The fact that it's called thermal energy and you know English probably means that this is associated with what? Heat, right? Okay. However, down at its core, heat is also related to motion. Okay? But it's motion on a real small scale. The energy associated with the movement of microscopic particles of an object. Now, when we're talking about microscopic particles, we're talking about microscopic particles, right? We're not talking about like cells and viruses and bacteria, right? We're talking about like atoms and molecules, okay? The very building blocks of matter. How much they move allows them to change other objects, or could allow them to change other objects. The more something moves, the more thermal energy it has. The less something moves, the less thermal energy it has. So the more, sorry, I shouldn't have said something. The more these particles move, the more that the atoms and the molecules that make up whatever object we're talking about move, the more damage that they can do, the more that they can change other objects. The less they move, the less they can change other objects. Good there? All right, the next kind of energy, while you may not be very familiar with it, is very important to you, and that is chemical energy. We will learn later on that these atoms that make up matter will join together in something that we call chemical bonds. And as they do, they actually release energy. but there's energy stored within those bonds. And under the right situation, we can take those atoms, split them apart, even though they were joined together, and when we split them apart, energy is released. This is really important to you because that's how your body works. Food is one form of chemical energy. You eat whatever you eat, right? Today for lunch I had cheese and wheat thins, an apple, and some baby carrots. That's what I had for lunch today. It's pretty exciting, I know. But so now my body, actually probably my body isn't hard at work breaking that stuff right down. It's probably breaking the bagel that I had for breakfast this morning down, right? But it's taking those bonds that exist within the food that we eat, breaking them apart, and as it breaks them apart, it uses that energy then to write physical science notes or walk through the hallway at school or have your heart beat or important things like that, you know. Okay? So, I mean, those were in order of importance, right? Physical science notes first, walking halls second, heart beating third. All right? So just make sure you know what's at the top of the list. Okay? But that's how it works, right? That's how your body works. It takes these atoms, splits them apart, uses that energy to do other stuff. Next, one that you probably aren't real familiar with, but is very important to our way of life and the way our society has sort of evolved, and that is electrical energy. I'm assuming most of you are at least familiar with electrical charges, right? Positive charge, negative charge, maybe, hopefully. If you're not, we're going to study some of that today, or this year. But two oppositely charged charges, positive charge, negative charge, what do they do to each other? They attract each other. Two like charges will repel each other, right? So same charged things repel, oppositely charged things attract. As those same charged things repel each other, or oppositely charged things attract each other, we can use that movement to then move or change other things, right? A battery or a cord that plugs into the outlet on the wall causes those charges to move. And as they move through, you know, a motorized car or your iPod or whatever it is, they can cause changes in other things, right? So that's another kind of energy, the ability to change stuff coming from these charged particles. Next, not to be confused, even though their names are pretty similar, right? Electromagnetic energy. Electromagnetic, oh, let's start with this. A lot of the energy that we get here on Earth actually comes from where? The sun, right? Now, Sean, what's between us and the sun? Pretty much nothing, right? There's a real small, thin little atmosphere that we have surrounding our planet, but most of the distance between us and the sun is nothing, right? It's a lot of nothing, about 93 million miles between us and the sun. There's a lot of nothingness there. But there has to be a way for that energy to get here. Certain forms of energy have the ability to travel as waves through space. They don't have to have anything carry them from one place to another. We refer to this as electromagnetic energy or electromagnetic radiation. We will discuss this in way more detail later on in the year, this transferring of energy through space, even though there's nothing there to carry it. One thing that always gets me when I talk about electromagnetic energy, especially light, is this number. And if you're watching on video, you're not going to see the number, so I'm writing it on the board, but this number, 186,000. Anybody know the significance of 186,000? Anybody? Sure? Oh, is that your hand or you're stretching? Okay. So, say again.
3.
Oh!
Sorry.
Correct. It is 3 significant digits. That's not what I meant with my question.
Oh.
It is 3 significant digits though, hold on. So, I was like, what's the significance of 3? Like what? I don't get it. So, but, no, this number is significant in another way. Not that kind of significant, but important in another way. Does anybody know the importance of said number? Yeah? That is how many miles that light travels in 1 second. Pretty fast. So, it's enough to go around the Earth about 6.5, 7 times every second. Okay? So energy travels through space really, really fast. But the other thing that always gets me about this number is that even though light is traveling this many miles every second, it still takes light from the sun about 8.5 minutes to get here. So we're talking about really big distances, the time and space part, right, how big this universe is, right? Even though light travels 186,000 miles per second, it still takes about 8.5 minutes for it to get here. So, you know, the sun might have blown up 5 minutes ago, but we won't know for another 3.5 minutes until the light gets here. So, live it up, I guess. I mean, so. But we will learn eventually, right? We will learn eventually that light is only one kind of electromagnetic radiation. There are lots of other kinds. X-rays, radio waves, ultraviolet, that all have this ability to change other objects, the ability to do stuff that travels through space. And then, one of my favorite units in the year is the nuclear energy units. Hopefully, you're at least somewhat familiar with an atom, and you know about what it kind of looks like. In the nucleus of the atom, we have parts called protons, and those protons have positive charges, and they are held together by something called a strong nuclear force, and we'll learn all about this as we go along. Okay? But if we get too many protons, then that nucleus can't be held together, and those protons will start repelling each other. And when that happens, it releases energy, which can be used to power nuclear energy plants here on Earth, or destroy Japanese cities, or whatever you want to do with it. So, you know, hopefully we don't use it for that, but there's a precedent there. So, okay. All right, good with our types of energy. Okay, tomorrow we will get more detail with mechanical energy, and we will talk about work that goes along with mechanical energy.